In this recording I'm going to solve a non-homogeneous second-order differential equation with constant coefficients and include two boundary conditions. I'm going to use the Laplace transform method. I'm going to solve it correctly to begin with and do some checks to make sure I've got the right solution. Then I'm going to backtrack and make an error in the process of solving. I will apply some checks and I will find that, crucially, one of the checks fails to identify the error. This will be a lesson to us in which checks to apply. This is an example of something which actually happened in an examination at our institution. So here we go. Here's the equation. I'm going to apply the Laplace transform to both sides of the equation. I will refer to the Laplace transform of the function x of t as capital X of t. So we get the following. I've applied the well-known formulae for the Laplace transform of derivatives of a function, which includes the boundary conditions. I now have to substitute those boundary condition values that are given in the original problem, and then rearrange the equation. After substituting the values for the boundary conditions and collecting the coefficients of capital X, then rearranging some stuff over to the right, this is what we end up with. I now need to divide both sides by the coefficient of capital X and then use partial fractions. Notice that in anticipation of the partial fraction process I have factorized the coefficient on the left as I've divided it underneath. I also have not bothered to reorganize everything over a single denominator on the right. It's not particularly necessary, and it can lead to errors, especially when under pressure in an exam. Let's now write down the partial fraction expansion for this mess on the right. It might look like this, for instance. I'm now going to multiply the black expression above and the blue expression below by all three of the factors in the denominators. I'll do this quickly, doing the cancellation as I go. Here's what we get. Stop and check it if you wish. We can get at the various values for a, b and c now by substituting s equals 3, 2 or -1. Let's do that in turn. First try s equals 3. On the left-hand side we will have 3 minus 4 and 3 plus 1. That will make -1 times 4. So -4. And there's 2 to add, so the left-hand side will be -2. The right-hand side is easier. Only the b term survives, and with s equals 3 we'll get b times 4 times 1, in other words 4b. That's easily solved to give the value for b. Now let's do s equals 2. I'll do this a bit quicker. This one gives us c equals 4/3. And then finally s equals -1. We get a equals 1/6. Let's put these three values back into the partial fractions. Here's the result for x of s, and it's now easy to take the inverse Laplace transforms of the three terms on the right to get little x of t as the solution to our differential equation. Here it is. And I don't know whether you noticed, but I have to confess that I had a sign wrong on that s minus 3 just above, and I've changed it from plus to minus. This is the correct solution now, with e to the plus 3t. So now we have what we claim to be the full solution for the dE with the boundary conditions. I want to check it, first of all by substituting it into the differential equation, and then by also checking the boundary conditions. To substitute this little x of t into the dE, we will need its first and second derivatives. Let's write them down now. Here they are. Pause the recording and check them if you wish. Let's remind ourselves what was the left-hand side of the differential equation. There it is at the top. The coefficients were 1, -5 and 6. I'll write it out again where we're working. we should now be able to substitute our three expressions in red here into the left-hand side and simplify to get the right-hand side. Let's try it. Look at how I make life easy for myself. I know that each of those exponentials has to appear as a factor in each of the three terms. Now all I have to do is look at the numbers 1, -5 and 6 and fill in the coefficients in the brackets. Let's do e to the minus t first. There is 1 of the second derivative, so that's a sixth. Then there is -5 of the first derivative, so that will make plus 5 over 6. Finally, there is 6 of the original x. That's 6 times a sixth, which is 1. I'm going to fill both the others in now. This is what they look like. It's now easy to simplify these. The first bracket, 1/6 plus 5/6, gives 1, and another one makes 2. So there'll be 2 e to the negative t. Ah, good, that is the right-hand side above. But the coefficients in the other brackets all cancel exactly. -3 is the same as -6 over 2. And so we've got -9 minus 6 is -15 over 2, and then add 15 over 2, so 0. Similarly, 24 and 16 make 40, and the other term cancels also. So the check has worked. We've reproduced the right-hand side. Let's now also check the boundary conditions. That just means substituting t equals 0 first into x and then into x dot. Do you remember the boundary conditions both had those quantities equal to 1? Here they are at the top again. X of 0 and x dot of 0 are both 1. 0 into x of t. Each of the exponentials will become 1, and that leaves us just the coefficients, a sixth, 4/3 and -1/2. Those do simplify to 1, so that's correct. Similarly, substituting t equals 0 into x dot, again we just get the appropriate coefficients, and again those simplify to 1. So all the checks have worked, and we can be confident that we have solved the differential equation correctly. I'm now going to go back to the solution process and introduce a simple error of a kind that just occasionally we see our students make when under great pressure. Here was the partial fraction algebra. I'm going to now get b wrong. Occasionally we get silly things like -2 equals 4b, and so b equals 4 over -2. It's wrong and rather careless, but I'm afraid it does sometimes happen. So let's go back to our solution and put b equals -2 instead of the -1/2 that we had before. We can go straight to the solution for little x of t. Bear in mind that b was the coefficient in the numerator of s minus 3 in the denominator. Here we are. We know this solution is wrong in advance, but I'm going to do the same checks as before. Here are the two derivatives, ready to evaluate the left-hand side. Let's now do that. Just as before, we'll get the three exponentials with various coefficients. Let's fill those in. We get these from the single second derivative, then the next three from -5 times the first derivative, and then we need to add in 6 of the original function. Of course, we only changed one thing, and that affected the e to the 3t, so the other coefficients we can expect to be exactly the same as they were before. The first one simplifies to 2, and the third one to 0. We would be hoping for the error to show up in the coefficient of e to the 3t, but oh dear, look, it doesn't. 30 take away 18 take away 12 is still 0. The whole thing has again simplified to the right-hand side, and we have failed to detect the error. Why do you think that's happened? Well, of course, it's because e to the 3t is in the complementary function. It doesn't matter what the coefficient of e to the 3t is. If you put it into the left-hand side, it will process to give 0, and a wrong coefficient there will not show up. There must be a way of detecting this error, so let's look at the boundary conditions for x. This time we get a result. It's the boundary conditions that manage to show up this error. Negative 7 over 2 is not equal to 1, of course. This is the boundary condition for x dot. I confess I've just slipped the dot on, I missed it before. Let's also check x though. When t is 0, x of 0 becomes negative half, which is also not equal to 1. So both the boundary conditions here have detected the error, whereas testing the differential equation did not detect it. That's a lesson for us, especially if we're in a hurry, for example in an exam. If we want to do a check, it's better to do the boundary conditions rather than the DE itself. Of course, if you've got time, try both, but if you have to give priority, make it the boundary conditions. They're usually easier to check, less work, and they have more chance of showing up an error. If both the boundary conditions work, you can probably be very confident that your solution is correct. This problem has been solved using Laplace transform methods, but of course the philosophy behind what I'm teaching here is the same however we solve it. It is still always more efficient and more reliable to check the boundary conditions first. They will show up an error quicker. I'll finish there.